Thanks a lot, Emily, for this very, very warm introduction. Thank you, the Perlmutter Institute. Also, thank you, CBC, IDEAS, and particularly Nala and Chris for hosting this event. It's always really great to be here, so thanks a lot. And I'll talk a little bit about the mysteries of gravity. We'll have an amazing discussion with Nala on the pursuit of gravity. But before I get there, I should start with a disclaimer that my field of research as a theoretical physicist is in that of cosmology, which, I'm sorry, for those of you who didn't know, is not to be confused with that of cosmetology. This is my Swiss slight delay in the jokes. So cosmetology is very interesting in itself, but it is the study of the universe of beauty, which some of you may be interested in. I think what's much more fascinating is actually the study of the whole universe itself, which is cosmology. Everything living in the universe since the beginning of time, if there was even such a thing, and since until the end of time. And so in exploring the mysteries of a universe, gravity is one of the phenomena that plays the most important role. And so we really need to understand gravity at a very fundamental level. And if you want to understand gravity, really appreciate gravity, you need to try to extract yourself from all other forces of nature. You need to embrace gravity and let yourself go to it entirely. And that may be quite challenging to do here on Earth, but if you imagine yourself, as we do, in outer space, maybe orbiting the Earth, then you can fall so freely that actually you don't feel anything at all, even though you are experiencing gravity. And you don't feel anything at all because every single particle in every single atom, in every single cell of your body, and the air in your spacesuit and the spacesuit itself are actually experiencing gravity in exactly the same way. This is something very universal about gravity. In fact, your cells are not torn or pushed apart. So there's no single cell in your body that can ever smell or taste or feel or hear gravity. Gravity is the most universal phenomenon that exists. It's a remarkable property about gravity, which we call the equivalence principle, and it is this universality of gravity that pushed Einstein to understand that there must be something more fundamental about it. If gravity affects everything and everyone in exactly the same way, it can't be encoded in the objects themselves, in the masses themselves. It has to be encoded in something deeper than all of us, in something that we are all experiencing, which is space and time. Nowadays, we understand, thanks to Einstein's theory of general relativity, that, for instance, the Earth curves the structure of space and time around itself, and we're all experiencing this curvature, and that's how we're experiencing the gravitational pull from the Earth. Now, the larger the mass, the larger the curvature, and the larger the gravitational pull. Now, throughout the universe, everything and everyone is connected to this space-time, and therefore experiencing this curvature of space-time and experiencing gravity. In fact, there's never such a thing as curvature at any single point. The very notion of curvature, and therefore the very notion of gravity, requires the connection of points with one another. You can think of the fabric of space-time as a patchwork of events in space and time, and gravity is a thread connecting between them. And for us, actually, I would say, here on Earth, on the surface of the Earth, I think this experience is quite tangible, because at any single point, we may have the impression that we're living in a flat patch, and for thousands of years, we thought that the Earth was flat. But actually, when we connect different points along a journey, this is where the curvature, in this instance, of the surface of the Earth emerges and folds. And then when you connect points along a curved surface, along a straight line. Those straight lines may look funny and curved from the outside, but that's actually just what a straight line looks like, adapting for the curvature of the reality in which we live in. And that's why, for instance, the orbit of, let's say, the moon around the Earth may seem curved, but actually the moon is just following a straight line in the curved reality, in the curved space-time of the solar system in which we live in. And when I say this, it may seem just like a cartoon picture, even a childish drawing of what gravity is like. But actually, this picture of gravity through the curvature of space-time is so profound, is so precise, that it has allowed us to predict the motion of the moon around the Earth within a millimeter precision. And just to give you an insight on how precise this is, if we wanted to do any better, we would need to account for leaves growing on the trees in the spring in one side of the hemisphere and falling down on the other side of the hemisphere and changing ever so slightly the distribution of masses around the Earth and how that affects the curvature in the solar system. This picture of gravity through the curvature of space and time is so precise that it has allowed us to predict the difference of flow in time as perceived by satellites on orbits above our head with what we're experiencing right here, right now on the ground. And this difference in the flow of time may seem very subtle, may seem very tiny and negligible, and yet it has remarkable consequences, for instance, for GPS positioning. If you registered for this event tonight, it is thanks to accounting for these very small corrections from the curvature of space-time and how we're experiencing it at different points in orbit for satellites and here. If you're listening to this through the radio, I can tell you we are accounting for those very small corrections. And so if you imagine the level of understanding of gravity we need to reach to even being able to positioning ourselves here on Earth and live the life that we are living right now on Earth, just imagine the level of precision that we need to reach in our understanding of gravity to describe the whole evolution and the whole behavior of our universe. And in fact, when we zoom into the largest possible distance scales, to the cosmological distance scales in our universe, we already have strong indications that our universe is behaving in, let's say, mysterious ways. For those of you who can see the screen, you'll see an animation zooming out of the solar system, zooming out of the galaxy, zooming out of a cluster of galaxies, over distances of billions of kilometers. It would take us just a few millions of years to get there if we were able to travel at the speed of light, which we can't, which we won't. And what we see on those huge distances is that it seems that all of the galaxies are distributed along clusters of galaxies, which looks like a little bit like filaments, embedded in halos of dark matter, and they're represented here in blue. These are just fake color. We don't see dark matter because we don't interact with dark matter. But it looks like most of the energy present in the universe is confined along the structure of masses in the universe. And if we look at how objects behave on those distances, what we would see, what cosmologists see, is that the further you look and the further objects seem to be moving away from us. And that happens in all possible directions. And that doesn't mean that there's something specific about us and about where we are and everybody wants to get away from us, which maybe, granted, that's a possibility. It simply means that actually the universe itself is expanding. What is happening is that the very structure of space is being stretched. And so anyone in the universe sees other objects moving away from them, and faster the further away they are. But if there's one thing we know about gravity, is that it is an attractive phenomenon. We are attracted by the Earth, for instance. And so if it were true that most of the energy present in the universe was under the shape, in the form of masses in galaxy clusters and dark matter, we would expect the gravitational pull from those structures to lead to a slowdown of the expansion of the universe. Maybe there could even come a point where the expansion of the universe has slowed down so much that it has come to a halt and the universe will start contracting. At least that's what we would expect if it were true that most of the energy budget in the universe was present in the structure. But over the past 25 years, cosmologists have actually seen exactly the opposite. What has been confirmed over the past 25 years is that the expansion of the universe is not slowing down, it's going faster and faster. The universe is expanding at an accelerated rate. And this is contrary to our expectation if it were true that most of the energy present in the universe was indeed localized in some structure of clusters of galaxies and filaments of dark matter. But if we were to zoom into a completely empty region of the universe, far, far away from any galaxy, from any stars, any planet, any particle, even far away from any dark matter halo, from any black hole, from anything at all, imagine how lonely you'd be there. In the middle of what we call a cosmic void, you'd be billions of light years away from anything else that you can see. And that you wouldn't be completely alone. Even in the middle of these cosmic voids, anywhere you are, even in the middle of emptiness, you still feel with some energy of what we call the vacuum. This is a quantum energy of the vacuum which fills every pocket of the universe uniformly from here on Earth to the middle of the cosmic voids. And in fact, the discovery of the Higgs boson is the proof that even empty space is filled with some energy, in this case, the energy of the Higgs field. It's a quantum energy of the Higgs field. And that energy has consequences on other particles. And if it has consequences on other particles, thanks to the equivalence principle, we would have expected it to have implications on gravity and therefore implications on the whole of the universe. And this is not per se controversial. It's almost known for about a century that we would have expected emptiness, empty space, to carry energy corresponding to the quantum fluctuations of the vacuum. Now, if we take Einstein's theory of general relativity, and we include this quantum vacuum energy, the good news is that it does lead to an accelerated expansion of the universe. The bad news, because there's always a bad news, is that the expected rate of acceleration of the universe from this quantum vacuum energy is way too fast. And is not just wrong by a factor 2, a small computational error that you can sweep under the rug. Actually, the expected rate of acceleration of the universe, thanks to the quantum vacuum energy, accounting for particles that we do know exist, for instance, the Higgs boson, is at least 28 orders of magnitude. This is the biggest discrepancy in the whole history of physics. This is the biggest discrepancy in the whole history of humanity. This would mean, if it were true, I'm a theorist, so I'm not very good with observations, but I can tell you there's one thing I know is not true. It would mean that the space between you and the person sitting next to you would be stretching so fast that it would go faster than the speed of light, and you wouldn't be able to see each other anymore. So, again, I'm a theorist, but I think that's wrong. I don't think that's happening. In phrasing the mysteries of a universe, we often phrase it as surprising that most of the energy budget of the universe is dark, and that components of the universe that we know exist, like you and me, and all of the standard matter, and stars, and black holes, etc., only make 5% of the energy budget of the universe. But the real question to my mind, the real puzzle to my mind, is not why is the universe so dark. The real question is why isn't it much darker? Why is vacuum energy not accounting for a much larger proportion of the energy budget of the universe as we would have expected? And faced with the biggest discrepancy in the whole history of humanity, I would say, the standard approach that you may hear of is simply to ignore the elephant in the room. This problem is so big that I'm simply not going to look at it. Maybe it's just going to go away. I'm just going to postulate for a reason or another that this whole hugeness of vacuum energy does not exist. I'm going to set it to 0 for an unknown reason that future generations are going to tell me. And instead, I'm going to postulate the existence of another, new kind of dark energy fluid, which has properties, actually, at the classical level that would have very similar properties to this vacuum energy. And that is the new driver for the cosmic acceleration of the universe. So that is one approach. And I'm going to go a bit crazy. But for the last few minutes, I'll try to postulate a slightly different approach. I like to go directly at the core of this problem. And I like to allow myself to consider this vacuum energy, which should be present, actually driving the acceleration expansion of the universe. Because it is there, it is naturally there. And so what I need to do is explain why this vacuum energy doesn't have as large an effect on the evolution of the universe as what I would have expected according to Einstein's theory of general relativity. In Einstein's theory of general relativity, we say that gravity has an infinite reach. This means that if I consider two objects located very far away from one another, let me just imagine two galaxies located on the other side of the observable universe from one another, some 10,000 million trillion kilometers away from one another. In Einstein's theory of general relativity, they still technically exert a small gravitational attraction on each other. Gravity is diluted more or less according to Einstein's square law, so there is a dilution there, but gravity never switches off entirely in Einstein's theory of general relativity. What's even more remarkable is that in order to describe the whole evolution of the universe, I need to account all of this vacuum energy that fills every pocket of the universe, and it is this huge effect that leads to this 28 orders of magnitude discrepancy between observations and expectations. But maybe this is just too much to ask. Could it be that gravity actually doesn't have an infinite reach, and I don't need to take all of this vacuum energy into account? If gravity had a finite reach, I would only need to account for a small proportion of this vacuum energy leading to the accelerated rate expansion of the universe. This range of gravity still has to be large. It still has to encompass the whole of the solar system and the whole of the galaxy and the whole of a local cluster of galaxy, but not an infinite range in itself. And having a phenomenon in nature that has a finite range, as I would like it to be here, is something that does happen. It is something that we have experienced in nature. The weak force in nature is a phenomenon that has a finite range, actually. It's a very natural perspective to have. In fact, the idea that gravity itself could have a finite range has been explored to some extent by many different scientists throughout the centuries. Newton himself contemplated the possibility that gravity, as he had it, could have a finite range. And Laplace after him, and many other scientists, and when people understood that gravity was through the manifestation of the curvature of space-time according to Einstein's theory of general relativity, and it had to be embedded into a quantum framework, people started exploring this possibility in that framework as well, including Pauli, who can be considered as one of the fathers of quantum physics, contemplated the possibility of having gravity in an Einstein sense, in a quantum sense also being a phenomenon with a finite reach. And this has happened throughout the past centuries, including Salam himself, who can be seen as one of the founders of the standard model of particle physics, one of the discoverers of the electroweak unification and the weak force, contemplated the possibility that gravity could have a finite reach. But this possibility has always been completely refuted, not because it wasn't consistent with observations, quite the opposite, considering a theory of gravity which have a finite reach would actually help us reconcile our expectations with our observations of the accelerated rate of expansion of the universe. It was because it was impossible to make it work theoretically. It was plagued with discrepancies which didn't seem to make sense in themselves until these two gentlemen came along, Gregory Gabadazzi and Andrew Tolley. And then with them, we managed to engineer a new architecture for gravity, a new model, which could, in some sense, displace all of these pathologies that were present in the other models. Now, the subtleties of that models are a little bit technical for right now. Maybe some of those equations will tell you something. But in a sense, the architecture of this model is not so dissimilar to what you can think of Penrose stairs or those type of Escher drawing of stairs, impossible stairs. What happens there is that you live in a confined space, and what we needed to do for a theory of gravity with a finite reach is to confine all of the pathologies in a confined, constrained space so they can do no harm. Of course, it's a little bit more technical than that, but that's the essence of it. In my mind, the trick in itself was pretty cute, but we soon came to realize that it wasn't sufficient to come with one mathematical proof that a model was consistent. To be sure, mathematics don't lie, and so if you come with one mathematical proof, then it must be correct. But even in science, there's as many languages and culture and different mathematical ways of phrasing things as there are individuals. And so over the years, every time someone came along with a different perspective, a different language, we had to adapt our logic into their way of thinking. We had to translate a mathematical language into a different one. And we had to repeat that over the years again and again and again until every single way to phrase the problem was consistent with our way of thinking about theory of gravity. But addressing that question in itself was never really the aim. The real aim in a theory of gravity is to confront it with observations. And if we are lucky, in the next few years, and maybe a decade or two, our understanding of gravity and observations on the nature of gravity will be so precise that we may be able to discriminate between a theory of Einstein's theory of general relativity, where gravity has an infinite reach, and a theory of gravity which has a finite reach, or which interacts slightly differently to account for dark energy. For instance, if you consider two stars or two black holes merging, they emit gravitational waves which distort space and time, and they travel for millions of years before reaching us on Earth. And we can detect them here on Earth. We have detected them already. Now, for a particular event, on the top is a type of signal that you may expect if gravity has an infinite reach, as would be the case in Einstein's theory of general relativity. And on the bottom is the type of signal you would expect if gravity had a finite reach, because gravitational waves of slightly different colors, of slightly different frequency, would travel ever so slightly differently, and so the signal we observe would appear more compressed. Now, by comparing what we would expect with what we actually observe, we could distinguish between a theory of gravity that has an infinite reach, as in Einstein's theory of general relativity, and a theory of gravity that has a finite reach. Whether the model of gravity that we have explored will survive those tests, we don't know yet. In a decade or so, we'll have very precise tests of gravity, for instance, thanks to the LISA space interferometer that you can see there, which will really allow us to understand gravity at a much precise level. Overall, whether a theory of massive gravity, the theory of gravity with a finite range that we have explored, and all sorts of different considerations, will be for future generations to tell. It's for them to tell whether they have any imprint on nature and any reason of being. But for now, I just want to contemplate the fact that just here, just right now, in this room, and I don't even know if it's day or dark anymore, and it can be sunny or raining, or sometimes it can be snowy in Canada, I've been told. There's gravitational waves reaching us all the time from the depth of the universe. And with them, they carry the most profound and remarkable messages. If we detect them, if we understand them, we'll may be able to understand if and how we connect with other objects located on the other side of the universe from us, some 10,000 million trillion kilometers away from us. Understanding those gravitational waves and the nature of gravity will allow us to better understand whether infinitely small fluctuations from emptiness that fill the whole of the universe uniformly from here on Earth to the middle of the cosmic voids lead to an evolution of the universe, help us understand the past of our universe, the present, and the fate of the universe, and everything living in it. So I'll stop here. Thank you.